So previously we have defined the bundle of KL tensors, but only as a set. We have never explicitly discussed the vector bundle structure. In other words, we haven't given a local trivialization. So let's do that. To that end, let's review the local trivialization of the tangent bundle and the cotangent bundle. Well, to find local trivializations of those bundles is the same as to find fiber coordinates. So let's talk about this in terms of coordinate. Since M is a manifold, at around any point P and M we should be able to find a neighborhood U on which there is some local coordinate given by a coordinate chart. Then these coordinate functions induce a basis of the tangent space to M at P. They also induce a basis of the cotangent space to M at P. And as P varies over U, this gives fiber coordinates on all the fibers over U. In other words, it gives a local trivialization. So what are these tangent vectors and covectors? Roughly speaking, the idea is as follows. So if we use this chart to identify this U with a neighborhood of in Rn, and let us take P tilde to denote the point corresponding to P, so this means P in coordinate, the coordinate of P, then under that identification, the tangent space and the cotangent space of this point at this point P can be identified with those at the point P tilde here in Rn. So these vectors and covectors are defined to be the one corresponding to these vectors and covectors under these correspondence. Remember, a tangent vector at P tilde here is just a derivation at P tilde, right? So this was just defined to be the usual taking a partial derivative with respect to xi, and this is defined to be its dual basis. That's roughly what the idea is. But now to be more concrete, let's actually define these explicitly. So let's define these as derivation on the germs of functions at P. So let's say we have a function f at P, a smooth function. How do we want to define this partial xi at P of f? Well, we want to use coordinate. So we will look at the coordinate version of f. If we identify U with this neighborhood in Rn, then f will correspond to a function which we call f tilde. We get f tilde by composing this inverse map with f. But we know how to differentiate functions from Rn to R. So we'll just define this to be the partial derivative of f tilde in the partial derivative with respect to xi, and then we evaluate that at P. So that gives us a definition of this basis of the tangent space to M at P. And now its dual basis is going to be a basis for the cotangent space. Thus, for every vector v in the tangent space at P, we can express it as a linear combination of these basis elements. So then the correspondence that sends every v to its coordinate here gives us a local trivialization of the tangent bundle over U. And that's the same with the cotangent bundle. So now let's come back and find a local trivializations for this tensor bundle. Remember, for the general case of any vector space V with this basis and this dual basis, then a basis for its space of KL tensor is formed by these elements. Now let's look at the case when V is a tangent space. Then, as we have said before, if xi's are local coordinate at P, then the tangent space and the cotangent space at P have these bases. Here we will denote this partial derivative by just partial I, just to make life simpler. Now then, so what's the basis for this space of KL tensor? Like before, a basis is given by these elements. I didn't write this at P part, that's implicit. And as before, as P ranges over U, this gives a local trivialization of the fibers over U. As they give coordinate in each fiber, they are what is so-called a local frame. But let's not worry about that for now. Now that we have had coordinates on these bundles, let's start doing some Germanian geometry.